So next topic is pulsars and neutron stars. So let's talk about neutron stars. Remember we talked about how if you have a core collapse supernova, so a high mass star that goes through creating heavy elements, we get a supernova, and as long as they're not too massive, we end up with a neutron star in the center. So basically somewhere in the 8 to 20 solar mass range. And what you're left with is something that needs to be less than 3 solar masses. So this actually forms if you have something that where the core is greater than 1.4 solar masses, so it exceeds the Chandrasekhar limit, you get something collapsing beyond electron degeneracy. And we talked about how basically it's getting so dense that the electrons and protons combine and form neutrons, and so you've got something that's just neutrons and a whole bunch of neutrinos, because that's what you need to form to balance the nuclear reactions, and then you get a neutron star. So what do we know about neutron stars? Well, they're going to be of the order of the size of a largish city, so 15 kilometers across. And here you can see it compared to a famous American city. The mass range is 1.4 to 3 solar masses. Below 1.4 you should get a white dwarf. Above 3 solar masses you should get a black hole, which we'll come back to later. And they typically have a density of 10 to the 14 grams per centimeter cubed. This is basically, it's made up of neutrons with essentially no space in between them, so it's at least as dense as the nucleus of an atom. And so, just to put this in perspective, I don't know if people are familiar with sugar cubes anymore, but basically a small die or something like that, you will get 100 million tons within this tiny, 1 centimeter cubed region. Okay, so remember we get core collapse, we get heating, it's so hot that it's no longer electron degenerate, so the neutron star when it forms is very, very hot. Its surface temperature is about that as the internal temperature of the sun. It's millions of Kelvin. It also has a very strong magnetic field. This is a weird thing about neutrons. Neutrons have a magnetic moment even though they do not have an electrical charge. It's actually something that people at MU take advantage of to use with the nuclear reactor down in the valley, where they use neutrons to investigate all sorts of materials because of its magnetic dipole. So it's got very, very strong magnetic field, a trillion times that of the sun's magnetic field. But also it's very, very small, so it's spinning very fast. Okay, remember that it's collapsed down from being, Earth-sized or more as a core, and it's down to the size of a city. So it's spinning very fast because angular momentum is conserved. But this means they're very difficult to observe. First of all, they are very, very hot. They're peaking in X-rays. That's where Wien's law would put the peak of the black body. But we can't observe X-rays from below the atmosphere. We have to be above the atmosphere. And even then, they're very, very small. And so we would not see them very easily just because the surface area is so small that they are very faint. Now, one of the things that was discovered almost 50 years ago was the idea of a pulsar. And this was something, it was actually Jocelyn Bell, who did not receive the Nobel Prize because her advisor took it. Jocelyn Bell discovered this thing that was producing pulses of radio waves on a very regular basis. So you can see here, this is the brightness in radio waves, and this is the time interval. You can see that, every few seconds you're getting another pulse. And since then we've discovered quite a lot more. And the period ranges from, milliseconds to a few seconds. But these are things that have been discovered all over the place. And we know they can't be white dwarfs, but how do we know that? Well, we need to consider how big a white dwarf is. A white dwarf is approximately the size of the Earth, so let's call it 6,000 kilometers radius. But we've got this white dwarf, we've got light coming to us, say we're over here. Light is coming from here, and from here, and from here. The stuff that's coming from over here has to travel a radius further than the stuff here in order to reach us. So it will arrive at us later. So it has to travel a further 6,000 kilometers, and it's traveling at the speed of light. and so it takes an extra 0.02 seconds. But that means that you would not be able to detect these millisecond pulsars. There just isn't enough resolution when you've got the pulse here is going to be at a different time from the pulse here. So we know that it can't be a white dwarf. And so the current model for what is giving rise to these pulsars is that it is a neutron star that behaves like a lighthouse. So what you've got is you've got this really strong magnetic field, and it's channeling radiation from the surface of the star to be beamed out through the poles of the magnetic field. And so what you get is something that is like a lighthouse. So basically it's spinning on its axis here, but its lighthouse is in this direction, so that means it's going around and around in this direction. And so if we are in the right direction, it will sweep past us occasionally. If we're in the wrong direction, we'll never ever see it. So there's almost certainly more out there than we can discover. But this is the basic idea. And so here you can see, and this isn't just radio waves, this is everything. So you've got light that's being beamed out, but then because you've got this very strong magnetic field, the light is being channeled into these cones, and so you get that light coming out, and it's light coming out at all wavelengths. Now, one of the things that's important to remember is that this is something that changes over time. It will weaken, it's getting less and less, and it starts off as a millisecond pulsar and gets slower and slower because it doesn't have an energy source, just like a white dwarf, and that energy is being beamed out, and the spinning is very fast. And if we don't happen to be in the line of sight of that jet, we're not going to see it. Oh, wrong way. So here we've got an image, and this is actually invisible light. So we've got, this is what the Crab Nebula looks like, invisible light, if you don't get a good view of the nice nebula. And this is what it looks like when the pulsar is pointing towards us. And so what we can see here is that it's also glowing invisible light. Here we've got the same thing, but now we're looking at it in the X-rays. So this was an image taken from a space telescope. It's in X-rays, and you can see it's switched off, it's switched on. And so, and this is showing you kind of a composite of all of that, so there seems to be a very complex structure associated with this tiny little neutron star that's spinning around. But it's also important that you can see this in lots of different wavelengths, so it's not just in radio waves. So here we see an X-ray image of a supernova in Puppis, and you can see that's the remains of the blown out star, and that's the remnant neutron star. You can see a close-up on it. Here we've got another one, and then this is Vela, I think. Yeah, Vela. And actually what you're seeing here, this is a bow shock. So this star is moving through the medium and causing a bow shock. And in fact, the neutron star, that this is the Crab Nebula, and it's in here, it is also moving. And so here this is an isolated neutron star, so this is one that's been observed but no longer has a nebula around it, so it's been around for a while. You can see here in 1996, and then again in spring 99 and later the same year, and it's moving in this direction. And so we know that these things, they're moving pretty fast with respect to the background stars. This is a proper motion, this is not something to do with parallax. So, just to summarize, pulsars are neutron stars. They emit light at all wavelengths at their magnetic poles. It's possible that the rotation axis will line up with the magnetic axis, in which case you won't get the lighthouse effect, but as long as they're offset, then you'll get this sweeping out of circular paths that we will see them occasionally. But we have to be on that line of sight. The pulsars are going to lose energy and slow down because they're rotating very fast. And that uses energy, and they're moving in space. And what this means is, if we look at the Crab Nebula, for instance, it's moving with respect to the shape of the Crab Nebula, and the one in Vela is moving with respect to its nebula. And what this tells us is that there must have been some sort of kick, that the explosion of the supernova wasn't symmetrical. If it was symmetrical, it wouldn't be moving with respect to the nebula. But if it's asymmetrical, then you can have a kick in one direction. And that's all we're going to say about pulsars, but there'll be a whole bunch of reading for you to do.